This is Mrs. O'Neill for AP Chemistry, Chapter 9, Section 2, the VSEPR Model. You should have watched the intro information video and taken some notes. Here are my notes, and I'll go through them briefly. So he talked about Lewis diagrams and the VSEPR models and how it helps us come up with the structure or the geometry, the shape of molecules. Nice flow chart as usual. He gave VSEPR a different acronym than it really stands for. He said they're valence electrons, you gotta add them up. You make your skeleton, which is basically a quick sketch of how you think the atoms are connected to each other. He talks about the electrons and which atoms are going to be more electronegative. He also talked about how many pairs of bonds there are, and then of course he reviewed the formal charges. So he took HCN as an example, again adding up those valence electrons according to the group numbers. He sketched out a skeleton model, how he predicted or thinks that the compound is going to look, and they usually, not always, but they usually give you the order, the molecule formula is usually the order of how they are bonded together. He also then talked about, things being happy, things being not happy, and of course we might have to shift bonds around, shift electron pairs around. So again, he kept going, then reviewing of those formal charges. Remember, it's the valence electrons minus the actual electrons to give you that formal charge. And in this case, the formal charge is 0 on all three elements, so that means they're all very, very happy. He went through another example of carbon dioxide, ozone. He also talked about resonance structure, talked about how the two oxygens that are bonded to that central oxygen is 1 and 2, but the one electron or the oxygen on the left could be double bonded or single bonded. So that's just resonance structure because each oxygen is its own oxygen. Then he really came up with what VSEPR really means. Valence, shell, electron pair, repulsion. So that's why we're always dealing with the valence electrons, and we have to deal with how those electrons repel each other in a molecule. He gave a nice balloon analogy. He also then again talked about carbon dioxide. He gave you bond angles and shapes all the way through, so I hope you were paying attention to that. So besides the actual Lewis diagram of the compound, you're also going to need to know its shape, and you're also going to need to know the bond angle. So if you did not pay attention the first time, you might want to replay this video and start drawing some of those out. And here's something extra. We're also going to be talking about hybridization. Hybridization is where orbitals are sharing those electrons, and all we do is label an electron domain. So we're going to label this S and this P, so we get an SP hybridization when it comes to a linear molecule and linear molecule. Here's a nitrate example. Again, 3 pairs of electrons. He shows you a nice visual of the resonance structure that also happens. Here he gives you the shape of trigonal planar and the bond angle. And of course, the extra would be labeling each electron domain. Each area where there's electrons or a bond gets an SPP, and that would be SP2 hybridization. Ozone, a third one. Now he talked a little bit more in detail about these lone pairs of electrons. This would be bent, okay? This would have a bent molecule because of those lone pairs of electrons pushing down on the other single and double bond there. Methane, again, this would be tetrahedral. It would have a 109.5 bond angle. And again, if we label each of those electron domains as SPPP, we would end up with SP3 hybridization. You can also have more electron pairs. He talked a little bit about trigonal, bipyramidal, and octahedral. And yes, you are going to need to know all of them eventually. So then he also talked about what can you build off of these models. Single bonds are different than double bonds, even though they both are considered an electron domain. He also talked a little bit about sigma and pi bonds. A single bond is also considered a sigma bond, and a double bond is considered a pi bond. Again, we will talk about that in more detail later. And then he just went on to everything is based off of that quantum theory. Again, where those electrons are in the atom. So back to your notes packet. Your objective for this particular section is how these molecular geometries can be predicted using this VSEPR model. And it's based, again, on those Lewis structures that we've been practicing drawing. And of course, it's the repulsions between those regions of electron density, or I like to say the regions are called electron domains. Again, pause the video, fill in the blanks, and then play to hear my words. So again, this VSEPR model allows us to predict the geometry. It gives these molecules a shape that we can understand why these electron pairs or bonds or double bonds or triple bonds are pushing everything else away from themselves. Remember that electrons repel themselves, so that's why they're going to be pushed as far away from each other as possible. So when we talk about these Lewis structures and determining the electron pairs, we're talking about bonding and non-bonding. So the bonding could be a single, double, or triple bond between two atoms, and a non-bonding, we actually call them lone pair or lone pairs of electrons. We want to remember that those lone pair of electrons actually take up more space than normal bonds. And when you see 3D models, you will see that that's really what happens. Those lone pair of electrons take up more space than a single, double, or triple bond. And we want to remember that multiple bonds, double and triple bonds, count as one electron domain or one electron pair. So an electron domain is anywhere electrons are most likely to be found. Again, you have your bonding electron domain, single, double, and triple, and you have your non-bonding or your lone pairs of electron. Again, electrons that are on one atom and not being bonded with anybody else. On page 333, and I will also have a handout for you, there's a list of electron domains. There's a list of what those bond angles would be, and of course the geometric shape. And these things we're going to kind of, I want to say, manipulate. Okay, so even though we talk about 3 electron domains, there's going to be a difference in the geometry, the molecular geometry, depending on how many are actually bonds and how many are non or lone pairs of electrons. So same thing, if you have 5 electron domains, that means 5 of them can be bonds. However, how about if you only have 4 bonds and 1 electron domain? The molecular shape is actually going to change, and we'll get into more detail as we go through this chapter. So how do we determine the molecular geometry? Well, again, first, we're going to draw the structure. You're going to count those pairs in the central atom as bonding or lone pairs. We're going to treat double and triple bonds as single bonds, okay, or single areas, single electron domains. We're going to determine the electron domain, how many there are, and then determine the geometry. So yes, you do need to know all of them, and yes, here they are in the book, just so you can see, have another visual. So this one has 2 electron domains, only 2 that are bonding, and it's got to be linear. So the shape is linear and the geometry is linear. So in the book, they're calling it non-bonding, but other places might also call it lone pairs. The other thing I want you to take notice is we're going to be doing a PhET lab. It's a lab simulation on the computer, and the shape is really the electron geometry, how many electron domains are around the central atom, and the molecular geometry is the geometry shape. Okay, so here we have again, we have the shape is based off of your electron geometry, or how many electron domains there are. So if you have 3 electron domains and all 3 are bonding, we're going to keep the geometry, the molecular geometry, as trigonal planar. However, when you have 2 bonds and 1 lone pair of electrons, so here's 2 bonds, but we have 1 lone pair of electron, we're going to call it bent. Okay, so there is going to be a difference between its electron domain shape and the geometry. Here is tetrahedral. You can look over the bonding and non-bonding and how that changes the geometry. Here is the trigonal bipyramidal. Again, now you have more options with your geometry because now you have 5 bonding, 4 bonding, 3 bonding, and 2 bonding, and that's going to change the number of non-bonding as well, and you really get complex geometries here. Again, you have an octahedral with 6 electron domains. And what I like about these slides, you might want to rewind a little bit. Look at the examples they give you, because those are some of the compounds that you're going to see again. Yes, you need to know them all. There's nice charts out there, and I have handouts for you as well. So I have this handout for you that shows you again the electron domains. This one is nice because it also shows you the hybridization of each one. It gives you a nice visual of your bonding with your elements and also bonding non-bonding pairs of electrons. I also have this one for you that's a little bit more in detail. It actually gives you the polarity, which we've talked about already, gives you the appearance. It also gives you the hybridization, but this is a 2-pager. So I will give you one of these. Please remind me if I haven't given it to you already, but it talks about your electron domains or your electron regions. This is a nice, just big snapshot, and then this one has a little bit more detail about those shapes. Also, if you'd like, you can go to this website, which I'll quickly go now, just to show you that it's a nice big chart. Don't go nuts and go through all of them, but you might want to click on 1 or 2 things here, and it really does a nice job of showing you a 3D model of that. Okay, and I think that's it. All right, see you in class.